Hey everybody, it's Mr. Zabo. So for day two of this learning target, we're going to continue talking about exponential growth and decay, but we're going to talk about specific types of growth and decay. Specifically, we're going to talk about compounding interest as opposed to simple interest. So as you can see on our first slide here in the first page of our notes, if we're investing $1,000 and we want to invest it for 5 years, regardless, we're hoping and assuming this is going to grow. This is an exponential growth model. And if I'm calculating simple interest, my equation looks like this. My interest, is equal to P, the principal, times the rate times the time. That's just calculating that 5% simple interest over that 5 years. So it's 5% times the number of years, with my principal being $1,000. That's the initial payment. So the equation looks like this. Our I here, our interest is $1,000, times 0.05 times 1. Over 1 year, it's $50 for a year. Over 5 years, so multiply that by 5. That's going to be $250. Simple interest calculation. So at the end of the 5 years, I have $1,250. But what we really want to focus on, that's not our exponential growth. As you can see, any input values are not as exponents here. What we want to look at is what compounded interest is really actually meaning. It means if I take my initial balance of $1,000 and I earn that $50 in the first year, I have a new balance to start my next year of $1,050. And so my 5% interest is not being applied to the initial $1,000 in year two. It's being applied to that initial $1,000 plus the interest from the year before. So now I have a 5% that's being paid on $1,050. And that pattern continues. So this is called compounding interest, when I earn interest on my interest. Hopefully it's easy to see that the better option is to earn interest on the interest. Now your money is earning money on itself. Money that you haven't invested but you have earned through interest is paying off with earning additional funds and additional interest. And you can see after 5 years in this example, instead of $1,250, we're at $1,276. So just over a 5-year time period, it made that big of a difference. $26 over a 5-year time period on $1,000 at 5% interest compounded definitely makes a difference. And we can make it even bigger if we wait a longer period of time, if we compound it more often. There's a lot of different variables that we can start messing around with. But for now, I want to go through and talk through the actual equation for compounded interest. Okay. So notice that this example of exponential growth, because the money is definitely increasing by that constant percentage, that 5% each year in that previous example, thus the 1.05 as our growth factor. Easier way to calculate this investment after 5 years is this equation. Okay. The A of t, my function notation, this is the ending amount after t years, so t being the input. Input being my exponent makes this an exponential function. Okay. Growth rate, we talked about growth being 1 plus r, 1 plus my interest rate. A is still the initial amount, so it's very similar to the equation that we've been looking at so far. Just defining this, instead of a times b to the power of x, it's a times 1 plus r. So we had already started looking at investigating that. So this shouldn't be all that foreign to you. In that example, the ending amount at 5 years was equal to this, all added into the one function here. Okay. And again, in the next slide here, we're just comparing this concept. Okay, A of t is equal to this. It's very similar to the original equation that we looked at. We're just saying that b is 1 plus r with an exponential growth function. Okay. Now, we can model exponential growth or decay with these functions. It's all just a matter of whether we're taking 1 plus r or 1 minus r. Growth, we're going to add our rate, and decay, we're going to subtract that rate. So if we know that we are growing, It's all a matter of whether we're adding or subtracting. So really just kind of nailing down, putting into some definition some of the stuff that we've already talked about here. If b is greater than 1, we have growth. If it's between 0 and 1, then we have decay. B and R are referred to as our growth factor or our growth rate. Um, and B and R, if it's decay, is decay factor or decay rate. Okay, so just understanding the difference between growth and decay. Again, you're focused on whether that number is bigger than 1 or between 0 and 1. Okay. Next example. As we look at this example here, we're going to suppose that we invest $500 in a savings account and it pays 3.5% annual interest. How much will it earn after 5 years? So it's really about picking everything out of this problem, recognizing what we know and what we don't know. In this case, what we know is that $500 is our initial amount, that's A, that our rate is 0.035. We're always going to take our percentage interest or our percentage rate of decay. We're going to write it as decimals. And we know our time is 0 or is 5. And we don't know the ending amount in our account. So we have these 4 variables. We know 3 of them. We can substitute in, type everything into our calculator. We can identify different pieces of our information if we were asked for that in delta math. Okay, we know it's growth because b is greater than 1, and we also know it's growth because we started with 500 and we're ending with $593. Okay. Example 2, similar concept. Now though, we know that we buy a savings bond for $25 and its interest rate of 4.2%. It's yearly interest rate, so attention to detail here is going to be really important. Okay, and what will the savings be worth after 15 years? So we know A, we know R, and we know T. We can plug those in and get $46. So $25 savings bond after 15 years is going to pay us out $46.34. Now, I'm going to say that you guys should probably just press pause and see what you can come up with on our example 3 here. So how'd you do? Did you get stuck? I hope so, because this one definitely is different. And so far, we actually don't know how to solve this. Hopefully, we did get stuck, though. I'm hoping that we got to the point we recognize this, and actually what we're looking for is the x value. We're looking for the amount of time. Now, I can isolate the base and exponent here by dividing both sides by 300, and I get this. But we have no algebra that we know of that we can solve this yet. That's coming in a very near future in a learning target that we will be attacking very shortly. Okay? But we can use our graphing calculators to solve this. Okay? And this is about solving this using we can use our table of values, we can use our graphs. Okay? I can set y1 equal to 5/3. That's going to get me a horizontal line through 5/3 on the y-axis, and set y2 equal to this exponential function, and identify a point of intersection. Okay, that means I'm going to have to adjust my window. You're looking at window, pressing X min, X max, identifying where your intersection is happening. In order to calculate an intersection, we have to be able to see the intersection on the window that we're looking at. Okay. Finding that intersection is second trace. Option 5 is intersect. And then you're hitting enter 3 times. That's going to find your intersection. It's going to give you your first curve, your second curve, and your guess or kind of identify the exact intersection of those two graphs. So in this case, they intersect at 11.6, 1.67. 11.6 is the x value. That's the answer that we're looking for. But it's not enough after 11 years, so you do have to round that up. Not because it's a 0.6, but you have to round that up because 11 years, even if it was 11.1, 11 years is not enough. You would have to say it would be after 11 years. It would be your 12 full years in order to achieve that $500. Okay, go ahead and see what you can do with example 4. So example 4 had two things that it's actually asking us to do. Ooh, I can go backwards here. Okay, it's asking us to find the value of the car, okay, in which case I know that if it's after 2 years, I know what t is equal to. And then separately, how many years will it be for the value to be $12,000? So that's a two-part question. First, let's answer after 2 years. Then we'll answer the second part. So first, I know that my time is 2. I know the initial amount. I know that the rate that it is decreasing, so make sure you have a subtraction problem here, okay, is 1 minus 0.16 at 16%. Okay. 24,000 times 0.84 to the second power gives me a value that's worth $16,934.40. Okay. Separately, how long will it take for this to be worth $12,000? Well, now I know A of t. I know that the final value is $12,000. What I don't know is how long it took to get there. I still have the same initial amount. I still have the same rate here. And I get to this point again, like we got to in example 3, where we do not have the algebra yet to solve this, so we are going to require us to use our graphing calculators for now. Okay? And I again recommend left side equals is your y1, right side of the equal sign is your y2. You might need to change your window. In this case, we didn't need to. Okay? We find our intersection using second trace 5. Enter, enter, enter. It's at 3.97, comma 0.5, which means 3.976 years or 4 years. Round that up. All right, so you guys have enough to go through and continue working on our delta math at this point. I would say that's your next step, making sure that you're watching the videos in there if you also need help, or you can certainly help each other as you're working through that in class.